Welcome to the lectures on fundamentals of MIMO wireless communications. We are discussing the MIMO channel properties. So we'll quickly take a look at the correlation properties that we have started with, and then proceed on to see the statistical properties of the MIMO channel, which are very vital for analysis of MIMO performance of MIMO communication systems, especially the diversity or the capacity links. So we have seen one of the most important things are the classical IID channel. This is one of the most important things that we have seen, and it's basically the H matrix, usually represented by the HW, which means spatially wide. And we have said that expected value of the elements of HWIJ, they are 0, and we have also said that the expected power of HWIJ are equal to 1, and finally expected value of HWIJ times HWMN conjugate is equal to 0, meaning they are uncorrelated. So it's a spatially wide for I not equal to M or J not equal to N. This is what we have said. We have also said that HW components are made up of X plus JY, where X and Y are independent and of 0 mean and same variance. So we have characterized them as 0 mean, circular, symmetric, complex, Gaussian. So this is the characterization that we have given, and we have also seen the spatial correlation. The first kind of spatial correlation we studied was with J0 2 pi delta x by lambda, which basically shows that if the two antennas are separated by a certain distance delta x, and the correlation falls as a function of delta x with respect to lambda in this fashion. And this is for uniform scattering, that means signals coming from all directions. If that is not the case, then you could capture the correlation in a different way, where we could say that the vec of H could be written as the correlation covariance matrix raised to the power of half times vec of HW, where we have explained the vec operation means vectorize. That means if there is a matrix A, which is A1, A2 up to AN, these are all columns. So vec of A would mean you put A1, A2 and so on, you stack them up. So once you have got this vec of H, then from this you can get H. So that is, the correlation is captured. We have also said that another simplified model to capture correlation is R to the power of half times RW RT to the power of half. That means this is the covariance matrix. This is the spatially wide matrix, which is started with the classical wide. This is the covariance matrix at the receiver side. This is that at the transmitter side, and this is how you would get it. Finally, if you would like to get R, that means this R from this R, you would have to get it by vec. This R is vec of H times vec of H Hermitian. This is how you would get it, and you could also get back R from RT and RR as RT transpose Kronecker product of RR, and where we said Kronecker product of a matrix A cross A Kronecker B would be given by A11 times the matrix B, A12 times the matrix B, A21 times the matrix B, and so on. So this is how the Kronecker product is, and you could relate the covariance matrix. So you start off with the classical IID, and from which you generate using this covariance matrix, you can generate H, which is of interest. So we will be getting most of our results for HW, but we'll be interested in H as well, because this is going to bring in changes to the system. But both of these are important. This is going to give us very important insights, whereas this is going to give us practical results in many cases. And while doing this, we would also be referring to the rank of a matrix. So rank of a matrix would mean if it's a rectangular matrix, the minimum of number of rows and columns if they are independent columns, and otherwise it is the number of non-zero rows or the number of independent columns. So the number of independent linear equations that can be formed would give the rank of the matrix. So what we will be using is a lot of matrix operations, and we'll just take a look at some of them at an appropriate time. So what you need at this point of time is to use some reference on linear algebra. We'll summarize some of the important results which will be used throughout the course. So when we look at the statistical properties of H, if H, let us write H as the matrix of our concern, then we could break H or factorize H into singular values of U, D and V Hermitian, where U and V are unitary matrices and D contains the diagonal of singular values with the properties that U Hermitian is equal to V Hermitian V is equal to I of size R. That means that the R is the rank of H. So if it is a square matrix and the columns are independent, then R is equal to size of the matrix, otherwise it is less than the size of the matrix. So this length is not equal to M. In that case, this length is equal to R. There are R components, the 0 components we don't write. You can always make a bigger matrix of the full size as H, but mostly we'll have it with respect to R's, and D is basically the diagonal containing sigma 1, sigma 2, sigma R. And we have said that we will make the criteria that sigma I is greater than or equal to 0, sigma I is greater than sigma I plus 1. That means it is an ordered matrix. Okay, and these are the singular matrices containing the singular vectors. And H Hermitian, that means H Hermitian product, this is MR cross MR, clearly because this is MR cross MT and this is MT cross MR. So basically this whole product is MR cross MR, positive semi-definite Hermitian, positive semi-definite Hermitian matrix, and it can be decomposed into Q lambda Q Hermitian, where Q are orthonormal matrices and lambda are the diagonal lambda 1, lambda 2, lambda MR, because there are MR, and also it is true lambda I is greater than or equal to 0, positive semi-definite. So semi-definite means each of the eigenvalues are greater than or equal to 0, lambda I greater than or equal to lambda I plus 1, that means it is ordered. And we also have lambda I is equal to sigma I squared if I is equal to 1 to up to R, and is equal to 0 if I is equal to R, R plus 1 up to MR, right. So this is what is going to be used. So we'll be mostly using these lambdas in our expression, and we'll be using this H Hermitian in most of our work. So as we go ahead further, what we have is H. If we take a look at H, the H contains elements H11, H12 and so on, H21, HMR1 up to HMRMT, right. So these are the contents of H. Now these are random variables, we have already said them. So these are zero mean, circular symmetric, complex Gaussian. So that means Hij could be written as X plus Jy, we have seen that, and these are varying with time, we have seen them. So basically this is Hi of t, what we have studied before, and this is Hq of t. So we have studied the properties of Hi and Hq, we have studied phi Hi Hq, phi of Hi, we have studied all these properties, and we have got this one follows Jake spectrum when equal angle of arrival, otherwise there is other spectrum, Rician's spectrum, and so on and so forth. So since what we essentially want to say that this contains random variables which have been very well studied, so this itself is a random matrix. So if H is random, what we have seen before, these lambda i's, these eigenvalues or the singular values, they must also be random, because whenever we look at this particular expression or we take a look at this expression that H Hermitian can be factored into this, the moment H is different, of course it's going to have different set of eigenvalues, and every realization of H will give us a different realization of the matrix lambda. So the matrix lambda contains these different eigenvalues, and hence all these would be different, and they would follow, and they would also be random. So what we are going to look at is some properties of this lambda and properties of H Hermitian. Okay, so if we take this, we would let us study the case where H is equal to HW. That means I am talking about the classical IID channel in which case I am referring to these conditions, the classical IID channels. That means each element expectation is 0, the power is 1, the elements are uncorrelated, and they are complex Gaussian. So this is the matrix that we are taking for our study. So if H is equal to HW, then elements of HW Hermitian are Wishart distributed. This is a particular distribution which doesn't look very simple, but this is useful to know. And the joint distribution, of lambda I, that means we are talking about the eigenvalues for HW channel. That means we are looking at the HW channel with, of course, we are making one assumption that MT is equal to MR is equal to M. That means we are making a square matrix assumption. This will be using square matrix for multiple reasons. Again, I'm iterating that we'll be using HW, will be using square matrix. The reason is we're going to get a direct insight into things. If we do not do that, and if we take different values of H, that means let's say we take H which is not classical IID channel, or we take the one which is rectangular, we are definitely going to get the results. The results won't look as straightforward or as simple if we take H as classical IID or as square. They would be cumbersome and they would not give us a direct insight into what the expression looks like. So whereas if we make these assumptions, we are going to get a picture, we are going to get a view of how it looks like. So that is very, very useful at certain times. Since we are trying to get an insight, we will make these assumptions. All the other cases are derivable from this assumption, so we need not really worry that we are using a square matrix assumption, so we will be limited in our understanding. Our understanding will be in fact better when we have this. All the results are derivative of this. There will be some modifications on top of this, but the fundamental results would be given by these things. We will see the variations when we take H instead of HW. That means we are taking correlation in the particular channel. So we proceed with this, and with this particular situation, the joint distribution of the lambda i's, that means f of x1, x2 up to xm, we are not writing mr or mt, we are writing xm, is given by a complex expression pi by 2 raised to the power of m squared minus 1 divided by gamma tilde m of m, this is a gamma function, squared e to the power of minus summation I equals to 1 to m xi, product of pi indicating product over I and j, but in the order I is less than j, 2 xi minus 2 xj unit step function u of xi indicating positive values, and gamma tilde m of m is the complex multivariate gamma function, and it is defined as gamma m of m is equal to pi to the power of m squared minus m divided by 2 m squared minus m divided by 2 pi of I equals 1 to m minus I plus 1 factorial. Okay, so this is together. So these two expressions together would define the joint distribution of lambdas. So from the joint distribution lambdas, of course, we can calculate all the things that will be required. The other important thing that we have is the smallest eigenvalue of HW Hermitian. What is that? We have lambda 1, lambda 2 up to lambda m. We have said lambda 1 is greater than or equal to lambda 2 greater than or equal to lambda m, and therefore lambda m is the smallest eigenvalue. So when we get these eigenvalues, they are ordered in this manner. So this is exponentially distributed. This is useful. So f of xm is given by m e to the power of minus m times m u of xm. Okay, so this is greater than or equal to 0. This is the indication. So what we have is these kind of things as the smallest eigenvalue. This is useful in calculating the outage probability, because when we talk of lambda, it's basically the eigenvalues of H Hermitian, and so basically it contains some kind of strength information about the channel. So if we take the minimum of it, that means we are talking about the minimum mode of the channel. And what we are saying here is that this is the strength of the minimum mode of the channel is distributed exponentially. So if we have to calculate the outage, we could probably use this expression in order to calculate the outage probability of the minimum mode of the channel. And so basically what it means is that the HW singular value, that means the singular, we are taken the lambda as the eigenvalue of H Hermitian, and lambda m is basically the minimum eigenvalue. So lambda m is equal to sigma m squared, right, going by our earlier description what we have said here. If you look at this, lambda I equals to sigma I squared for I equals 1 to r, and equals to 0 for r up to mr. And here we have said we are taking HW. We have said HW is the specially wide channel of full rank with probability 1. So therefore r is equal to mr. We have said mr is equal to mt equals to m. So that means this equation holds for I equals 1 to m. So lambda I is sigma I squared. So that is what it is. So this is exponential distributed. In that case, sigma m would be Rayleigh distributed. So this is again another important result which can help us in understanding some of the properties of performance of MIMO communication system. So these are some of the important results. We move on further and we take a look at the squared Frobenius norm of H. So it is indicated by H with double lines on both the side, a square on top, and below F indicating Frobenius norm, squared Frobenius norm of H, which is defined as HF squared is equal to trace of, trace is a matrix operation of H Hermitian. We have explained what is Hermitian operation. Hermitian operation is the transpose with the complex conjugation, which is equal to I is equal to 1 to mr, j equals 1 to mt, and hij mod squared. So if you take a look at this, j is going from 1 to mt, I is going from 1 to mr, and we have hij. That means we are covering all the channel coefficients. And if we take a look at this, hij squared is basically the strength of the ij component. So if we have h12, h11, h12, h13, and so on, h21 up to hm1, finally hmm in case of hw channel, otherwise mr1, mrmt. So this squared plus this squared plus this squared plus this squared, so all of them squared. So what we are getting is the strength of the channel. So this is in other words, this is can be interpreted as the total power gain of the channel. This could be one way of expressing this, and we also have the expression hf squared is equal to I equals to 1 to mr lambda I. That means you are adding up all the eigenvalues. So that is again from the trace of H Hermitian. Trace of H Hermitian is the sum of all the eigenvalues, where lambda I is are the eigenvalues of H Hermitian. So again, just have a look at this. Since lambda i's are random, this we have said previously, this is also random naturally, because H is random. H leads to lambda i's being random. If lambda i's are random, this whole sum is random, and therefore this is also random. So this is also a random variable, and the statistical properties, the statistics of H f squared determines the diversity performance of MIMO systems. We will see how. I mean, this is very important random variable, and if you take the PDF of HW, that means if you take the PDF of HF squared when H is equal to HW, right? So we are taking for the specially wide channel. We could write Fx as x raised to the power of mt mr minus 1 divided by mt mr minus 1 factorial e to the power of minus x u of x. Okay. So this is always positive 0 greater than or equal to 0, 0 only when this is equal to 0. So the expression for the PDF is this, and therefore we could say that HF squared is chi-squared distributed, and with 2 times mt mr degrees of freedom. Why do we say so? Because if we take a look at this, let's take a look at this one, Hij squared. So Hij squared is basically, we could write it as Hij of t, if you remember mod squared. So this Hij of t is complex Gaussian, it is 0 mean, and it is circular symmetric. Complex Gaussian because Hij could be written as H capital I of t plus H capital Q of t, indicating that there is a I component, there is a Q component, of course there is a J. We have studied the statistics. 0 mean we have seen, so they are Rayleigh distributed. Circular symmetric because these are independent of equal variance. So if this is Rayleigh, this whole thing is chi-square distributed with 2 degrees of freedom, first degree and the second degree. And how many of them are there? Mr and mt are there. So mr times mt times 2, so that means 2 mr mt degrees of freedom of chi-square distribution. So this is one of the important things that we need to know, and we may be using them. And the quantity of interest to calculate the diversity function. It's when you are calculating the diversity performance of MIMO communication systems, we would be using the moment generating function. This is quite useful, especially when you are calculating the BER. So there are different ways of calculating the BER, but one particular result exists which is often quite useful in giving this performance. So we denote it, I mean, if moment generating function of the random variable, we are interested in HF squared, and if we write it as psi of HF squared of, let's say, nu, this is how we are going to represent it. Okay. So assuming Rayleigh fading, so we'll assume Rayleigh in Hij, we could say R, the covariance matrix, is expectation of the vec of H. This we have already seen, vec of H Hermitian. This we have already seen this expression, right? So this is the covariance matrix of H, and psi of HF squared of nu is given as expectation of e to the power of minus nu HF squared. Now in some cases you could write it as e to the power of nu HF squared. It's all the same. It depends on what we do at the end. So this has been evaluated. It's not a very straightforward evaluation. So if this is evaluated for the Rayleigh fading, this one turns out as 1 by determinant of I matrix. I is the identity matrix of size mt mr plus nu times r. If it is plus over here, you're going to get 1 by determinant I mt mr naturally, a minus nu times the lambda I, this is times nu of r. Now if you look at this, the determinant, we could write it as product of I equals to 1 to mt mr 1 by, since this is the I matrix, 1 plus nu times lambda I of R. The size of R is MRMT because this is vec. Vec means H is MR cross MT. So vec of H is MR MT cross 1. This is 1 cross MR MT. So this is basically MR MT of the size MR MT. So the determinant is the product of the eigenvalues, and product of the eigenvalues would mean that lambda i's are the eigenvalues. This matrix is an I matrix, that means it is 1 1 1 1 and zeros elsewhere, right. So basically the diagonal entries get this 1 added to it. So the determinant can be formed in this fashion. So once we are writing this, this particular expression is going to help us in calculating the diversity performance, because we will be often getting expressions of this order, which will be very, very useful. So what we need to note is we have to use the eigenvalues of R, and we have to find this variable nu or v, which will be very much helpful in calculating the psi of nu, and they will be replacing nu with the appropriate value, and we will be able to calculate our error probability expression. So to summarize, what we have done is primarily the most important thing we have looked at in this particular session is the squared Frobenius norm, and how we have derived how we have found what is squared Frobenius norm. So squared Frobenius norm is basically the total strength of the channel, and if you look at the moment generating function of HF squared, it turns out to be of the structure which is product of 1 over 1 plus nu times lambda I R, where nu is given in the psi is given by this expression. So I have already said this could be a minus, this will become a plus. If there is a plus over here, it would become a minus over here. It just doesn't matter basically, because this whole expression will be used. So the sign is unimportant in our case. So we'll be using this for calculation of probability of error, which is again a very, very important expression for use. We'll be using this in the future lectures on performance calculation of diversity schemes in MIMO. Thank you.